My name is Mikko Ritala. I'm coming from University of Helsinki and Department of Chemistry, and I was asked to give you a presentation about ALD MLD chemistry, and the outline of my talk is shown roughly here. So I will first make some general comments about ALD MLD chemistry. We have heard that quite a bit already in the morning today, but still make some comparison against CVD chemistry. Then we'll go through in quite much detail the requirements for the precursors in ALD MLD, and then make kind of a general survey about these common precursor types that have been used in ALD. I'm not including here the organic molecules for the reason that I guess that Ulla can't talk about MLD without talking about the chemistry quite a lot as well. So my focus is mostly on the ALD side. I also like to talk more about ALD than MLD because I've been working with ALD now 27 years, so I have some experience on that. My personal touch to MLD is quite thin against that one. Okay, so before I start, so let me tell you about one recognition which was awarded to the inventor of ALD, the Finnish inventor of ALD, Tuomo Suntola, this spring, May, more specifically. And at the same time, the prize was given to him, but he and I think we all kind of join him in thinking that this was also a recognition to the ALD community in general. So this is about the Millennium Technology Prize. It's kind of a Finnish counterpart for the Nobel Prize. This is for the technology. It's given every other year, and this year it was awarded to Tuomo Suntola for his achievements in ALD technology, getting it started, and the kind of a justification for this prize was coming from the importance of ALD, how it's behind all the microelectronics today being produced, as Christoph was talking about that in the morning. So the prize was awarded by our President Sauli Niinistö. To put that into a perspective, here is a list of the previous Millennium Technology Prize winners and the topics for these awards there as well. So it started from Tim Berners-Lee, World Wide Web, Shuichi Nakamura about these LEDs, Robert Langer, Michael Kretzel, very well-known names there, and now Tuomo Suntola is the latest award winner here. The prize is for €1 million, so it's not a very small prize either. And as explained, so it's given for the extensive impacts of science and technological innovations on societies, even on humanity at large scale. And really the reasoning justification for Suntola getting this prize is coming from this kind of a curves, which Christoph to some extent showed already. So during the past, actually starting from the turn of the millennium, ALD has been expanding a lot, no matter what kind of indicators we are using in measuring them. These are the scientific publications. This is the market size of ALD tools, exceeding now $1 billion. Here are applications of ALD in semiconductor manufacturing, trying to show that there are more and more all the time coming up, and scaling trends. So when going to the next generations in semiconductor industry, it's been estimated that the number of processing steps exploiting ALD will double. So ALD really has become an important technique, so no matter whether we are looking at these curves or the Millennium Technology Prize. And now the question is, so can we together bring also MLD to the same level in the future? This morning made it very clear that the success of ALD and also MLD in the future will be built on chemistry. So there are lots of very nice features about ALD: conformality, large area uniformity, thickness control, and so on, which are built on the self-limiting saturated surface case, which means that to exploit these benefits for a given material, one always needs to identify and find the right kind of precursors which are fulfilling these ALD kind of or requirements for the ALD precursors. So meaning that they are undergoing these saturative surface reactions, because only that makes the film growth. Self-limiting, and only self-limiting film growth then translates into these advantages, features of ALD. So when talking about ALD, MLD chemistry, so one can roughly group these as shown here. So if one is using metal precursor and some non-metal precursor, then one is depositing inorganic films, either compounds or elements. That's what we are nowadays calling ALD. On the other hand, so if one is replacing one or two of these precursors with organic molecules, so then we are actually coming into the domain of what is now called MLD. So either depositing hybrid materials or organic polymer films. Exactly like Ulla was talking before the flux. One can also mix these things in various manners, so one can add other reactants, so third, even more reactants into these processes here, or one can combine these in different ways, either to make mixture films, so completely mixing 2 or 3 thin film materials, or creating nanolaminate structures like shown here, for example, for tantalum oxide and polyethylene. So now, because ALD can be seen as a modification of chemical vapor deposition, it's kind of sort of emerged from that side here. So there are still a lot of similarities between CVD chemistry and the ALD MLD chemistry. But there are also some very important differences which are now picked up here. So these are actually consequences about the special characteristics of ALD, so alternate pulsing and the requirement to have self-limiting, self-terminating surface reactions. So alternate supplying of the precursors, so the good news here is that we don't need to worry about gas-phase reactions. In CVD they may start creating particles if they are too readily occurring. On the other hand, the negative news here is that we don't have kind of a competing reactions if there are possibilities for etching reactions to take place. I will show you some examples about those later. And then kind of a just neutral statement or observation here is that even more important than in CVD, in ALD, surface groups play a very important role in the overall film growth process, because it's only through these intermediates how these two precursors can actually come into contact with each other. Self-limiting growth means, well, kind of a negative thing here is that it limits the choice of precursors, so that we need to find precursors that are not decomposing on their own. If they are decomposing on their own, we are losing the self-limiting growth. On the other hand, so the good news from this is that we don't need to have strictly uniform precursor fluxes to produce uniform films. This applies both spatially, so we can have a larger dose in some part of the substrate than the other part, as long as we are saturating all the surface reactions. It also applies temporally, so meaning that the very first pulse as it's open is can be larger than the very last one pulse in the given process, as long, again, also the last pulse is high enough to saturate all the surface sites there, and that then ensures that we still get the same amount of film being deposited also in the last cycle as in the first cycle. That means that one can more readily exploit solid precursors in ALD than in CVD. In CVD, there is a problem that once we are heating these precursors, they are sintering, their surface area is changing, the flux coming out from the sources is changing, and that causes trouble. It's to some extent problematic also in ALD, but still easier to tolerate than in CVD. So this is now the list of precursor requirements to ALD and also MLD precursors. I've divided that in two parts. So the first part is really kind of a must. You need to have these requirements fulfilled to have a true ALD or MLD process. On the other hand, the lower part here, so this is something nice to have, so to make life easier, so you perhaps prefer to have cheap precursors, easy to handle, non-hazardous, and so on. But quite often it is so that you can't get that all, and then it's more or less this lower group that needs to be compromised to build up an ALD, MLD process. Now I will go through these one by one and a little bit opening them further. So volatility is quite obvious. ALD is a vapor phase technique, so to bring the precursors over the substrate surface, we need to transfer them into the vapor phase. What is volatile enough? So that's a little bit more tricky question, but roughly speaking, so at least we are using so that it should be something like 0.1 torr or 0.1 millibar at the applicable maximum source temperature, which then of course depends on the reactors what you are using. I will show examples of that in the next slides. Of course, if there is a need to deposit ALD films over large areas, so large substrates or large batches, so then also the vapor pressure requirement goes up. But in research scale, this is something we can live with. And yeah, as I said, so the maximum source temperature, that's very much depending on what kind of a reactor you are using. Liquids and gases are preferred also in ALD. They are easier to handle. They don't create particle problems the same way as solids, but quite often there is a need still to go with solids, and they are acceptable as well, but one needs to know there is some issues which are related. So this sintering and also the fact that if your solid is consists of very small particles, so these gases, even if we are working at somewhere about 5 millibar regime or so they may be transported with the gases from the sources towards the substrate, and there they could create defects. So the valuing mechanism is very critical for that. So what is the maximum source temperature one can use to evaporate the precursors? The best one can get is actually shown here. So this is inert gas valving, and our group is more or less spoiled to have that available. I don't have time or need to go into details here, but in inert gas valving, so the valving action, so determining where the precursor is coming out from the source or not, so that's realized by controlling gas flows in between the source and the chamber. And these flows can be controlled by mechanical valves, which are themselves at room temperature, yet the valving action itself is there at the temperature where the film growth itself is taking place. So it means that it can go up to 500 centigrade or actually even higher in our research scale reactors. On the other hand, if the next option is to have just kind of a mechanical valves, nowadays these are available for high temperature operation, at least up to 300 centigrade. Maybe there is already one model which goes up to 350 centigrade. They are a little bit more complicated to operate and install, but once they are there, so this is now then the upper limit for the source temperature. Yet another way to deal with these low volatility precursors is to have liquid injection, where one makes, if talking about low vapor pressure solid, so one chooses a proper solvent to which this compound is dissolved, and then this solution is injected into a heated vaporizer where both the solvent and the compound itself is evaporating, and then transported further to the substrate. And then, in principle at least, so here one can moderate at reasonably low volatility compounds. There are some problems, of course, related to the fact that one still has these low vapor pressure solids there, and there may be a number of issues. Anyhow, these kind of liquid injectors, they are also commercially available, and I think we will hear more about these later today still. But then the factors which are affecting the volatility. So it's not very straightforward to think or reason so how, for example, a given compound, so how volatile that would be. But there are some sort of a rule of thumb in general. So light molecules in general, they are more volatile than heavier molecules. That means, for example, then in case of metal precursors, that one should avoid the fact that metal precursors quite often they form dimers, trimers, or even higher oligomers. So one should try to control that by choosing such ligands that shield the metal against oligomerization. Meaning sterically demanding of bulky ligands, polydentate ligands. I will show you examples about this as we proceed. Another thing, so this is molecular structure and weight. Another thing there is one should think about, so how these molecules are interacting in the condensate. So preferably interactions from one molecule to the other one should be weak, because that means then low lattice energy and easier volatilization. So one should find molecules where the bonding is quite covalent, so that there would be only low dipole moments in the molecules, because if there are large dipoles in the molecules, there is a lot of dipole-dipole interactions. But these should be avoided, and if so, one has a better chance to make volatile precursors. There's also one quite common way with metal precursors has been to play with fluorinated ligands, so one adds fluorine into the ligands, and as a result creates sort of ionic type of interactions between fluorine to fluorine from one molecule to the other, decreasing the interaction rate. But really the molecular structure and weights, this is very important for the MLD precursors, for these organic molecules. So that what we have so far studied, and it's brought the possibilities to choose precursors for MLD, has taught us that quite rapidly we actually reach such molecular sizes that the volatility really becomes a limiting factor in using these precursor molecules. And that's obviously something we need to deal with in HYCOAT quite a lot in the future as well. So this is one very simple textbook kind of example about the dimerization effect and how to control that to increase the volatility. So tantalum methoxide is a very commonly used precursor in ALD. In its simple form, but when we're talking about tantalum methoxide as such, so that actually is a dimer. The structure looks something like this one. Why it forms a dimer is that tantalum prefers to have coordination number of 6 or perhaps even higher. And in this, if this would be just a monomer, the coordination number obviously would be 5. So by making a dimer, so both tantalum atoms here are increasing their coordination number to 6, and they are happier in the environment. But that means that this molecular weight for this dimer is obviously it's doubled because of this dimerization. Now, by simply changing one of the ethoxide ligands to this kind of a, well, it's an amino ethoxide ligand. So now we have in this ligand we have 2 donor atoms which can bond to the tantalum. So oxygen, as in the other ligands, but also nitrogen. And as a result, so this requirement of coordination number to expand to 6 becomes fulfilled already in a monomeric precursor. And as a result, so molecular weight is lower, and that is translated now to the higher vapor pressure for this donor functionalized alkoxide as compared to the parent alkoxide itself. So these are very kind of simple tricks as such to increase the volatility. How then the volatility can be examined? Ideally, it would be nice to have vapor pressure measured for every single molecule we consider to be used in ALD or MLD. But that's not the case for the reason that vapor pressure measurements are quite complicated to do, especially when talking about low vapor pressure compounds. In such cases, the common tool is thermogravimetric analysis. So that basically is an instrument which measures a mass of a sample as a function of temperature. And typically this is done so that one is increasing the temperature with a constant rate. One can also do it so that one keeps the temperature fixed and then measures over time, so how linearly the mass is decreasing because of volatilization or not. But in most cases, it's this kind of a ramping of temperature towards higher temperature. This can be done under inert gas at normal pressure or under reduced pressure. These normal pressure measurements, they are much more simple to do, and as a result that these are quite often, for example in our case, our group are being done at atmospheric pressure, even if they are not exactly so relevant to the ALD conditions where we are working at under reduced pressure conditions. Anyhow, no matter what is the pressure there, so from these curves we can distinguish whether there is a complete volatilization in one step. So for example, this solid curve here is showing what one wants to see from a good ALD precursor or MLD precursor. So it very nicely, once reaching a temperature where evaporation starts and going towards higher temperature, everything gets volatilized in one single step. That's an indication of, well, nicely volatilizing precursor. Sometimes there may be, I saw in the next slide, an example so that there are actually several steps, so there is some transition in between, but eventually everything gets volatilized, so there is a zero residue being left. But sometimes we see curves like this one, so that there are a couple of steps, and in this case the residue is something like 30%. This is an indication that most likely this is not very good ALD MLD precursor. So there seems to be partial decomposition to take place already during the volatilization. So here is an old example about precursor which is actually, eventually it is completely evaporated, but there is a step in between. So the starting compound here is zinc acetate dihydrate. What happens here in the first step actually is that these water molecules, they are released, and also there is a reorganization of the ligands around the zinc atoms there in a molecule. It forms a tetramer, which looks like that one. It's actually quite heavy, and as such not very attractive ALD precursor, but anyhow, this can be volatilized once going to high enough temperature so that zero residue is left. Then on this side here, so there is an example. This is actually from Bochum, paper from Bochum, so for iron precursor, and its TG shows that there is first volatilization starts nicely, but it doesn't go all the way to the zero residue. So seems that there is some decomposition taking place simultaneously together with the evaporation. And indeed, in ALD experiments, they saw that this compound seems to start to decompose around 175 centigrades. That's why actually there was some measurements also under these isothermal conditions. So at 80 centigrades, 100 centigrades, and in this case, or actually both cases, one sees that there is a linear mass drop as a function of time when this compound is kept at these temperatures. And of course, the mass drop is faster when going to higher temperatures, which gives a kind of indication and promise that even if this is not completely ideal, this normal TG curve, so one can still use this compound so that one chooses these temperatures as source temperatures and stays below 175 centigrades. So it's quite narrow window, but still there is a hope to get something done with the precursor anyhow. So when you are reading through literature, so you see a lot of TG curves. I mean, most likely you can also find a TG curve which is measured by different groups for the same compound, and they look different. Which one is right? Actually, they both are right. So it's very important to understand that the TG curves, so how they look like, so they depend on several factors which are mentioned here. For example, heating rate. Actually, we saw an example here. In this case, when heating was done with slow rate, so there was enough time for everything to evaporate before decomposition started. But now if the heating was done 8 times faster, actually one doesn't get any more zero residue for the reason that when reaching the temperature where decomposition starts, so there is still quite a lot of material in the TG crucible, and decomposition starts to affect the result here. So slower heating rate gives sort of a better result in that sense. Pressure affects also how rapidly the evaporation takes place. So here are two curves. So one is measured at normal pressure, and this one is at 5 millibars, which is the ALD reactor operation pressure in our case at least. And one can see that under reduced pressure, so evaporation starts to take place already at about 110 or so, whereas at normal pressure there is hardly any mass drop yet. So this is simply a consequence of different pressures. Also, what is the gas phase flowing over the crucibles? That may have an effect there. So it should be inert when studying the volatilization, but if there are some reactive components in the gas stream, either by purpose or accidentally, these reactive components, of course, can then start reacting with the compound and affect the evaporation behavior. Thermal balance configuration has an effect there as well, and also the crucible. So in principle, one can do TG measurements so that one has an open crucible. Then, of course, what evaporates can easily come off and be swapped off from the balance with the gas stream. But sometimes one may also add a cover there. And as a result, so now what evaporates actually stays still in the crucible, and if then reaching higher temperatures, so can start decomposing there. And this, of course, affects quite a lot, so the outcome of this. So the main message here is that when comparing TG curves, you should always do the comparison for such results which have been obtained under exactly the same conditions. So most preferably you measure those what you want to compare in a sequence after one after each other, to be sure that you are really comparing the right things. Okay, then next requirement is to have aggressive reactions. Why we need aggressive reactions there is that ALD is low. How can we make it faster is to saturate the surfaces in as short time as possible, and by choosing precursors which react aggressively with the surface intermediates left by the other precursor, one can shorten the cycle times, and by that way one can also increase the throughput. Aggressive reactions usually also mean that the reactions are complete, so that is then leading to high film purity. We don't need to worry about gas phase reactions, as already said, because these precursors are not at the same time in the gas phase. And as said already, so very important is that the reactivity is high also towards the surface intermediates left by the other precursor. Thermodynamically, this means that one is looking for reactions that have as negative Gibbs energy change as possible. Sometimes, especially when using inorganic precursors, so we have thermodynamic data available and we can easily calculate these Gibbs energy changes. Unfortunately, when making new precursor molecules, we don't have the data available, and then, well, we can't use this criteria. Christoph already showed you what happened with these alkyl compounds when exposed to air. So this is TMA leaking out from the cylinder. This is probably where somebody has tried to add water on top, so that's not a good idea. Christoph didn't say what to do when fire breaks out, so you should use sand or some vermiculite or other materials which are not reactive, and just prevent then oxygen and moisture vapor getting in contact with these precursors. And once you have done that, so you should carry it out, and remember and notice that whenever you scratch this sand, so it will start burning again. So you just need to burn it away, so that's the way how to handle it, but in a controlled manner. Titanium chloride it's not burning, but it's producing this kind of a solid fume while reacting with moisture. So these are a little bit scary things, but the true fact is that these are good signs for a good precursor for oxide ALD at least. Okay, this self-decomposition I already expressed. We can't have that because we want to have self-terminating surface reactions. And if we are losing this requirement, so then we start to observe thickness non-uniformity, inaccuracy in controlling the film thicknesses, perhaps conformality, and so on. In general, it's thought that every time there is a decomposition, there are also impurities being incorporated into the films, but that's not necessarily the case. Because in ALD, for example, if you are depositing oxides, so you may use a precursor which is a little bit decomposing, leaving maybe some carbon there, but the next thing what happens is that you may have an ozone pulse coming over, and that will clean away major part of these impurities. Sometimes the decomposition indeed leads into contamination, but not always. On the other hand, we don't need to be strictly ALD in many cases or for many applications. If you think about, for example, corrosion protection coatings, they don't need to be exactly uniform all over the large parts there. We can accept some CVD component on top of ALD component, provided that the decomposition results in the same product as the ALD reaction. For example, titanium alkoxides are used together with water to deposit titanium oxide by ALD, but if going to too high temperatures, they start to decompose on their own, producing the same titanium dioxide. And if this makes only a small contribution to the total flow rate, so one has a still reasonably good control over the whole thing. And well, basically this is valid when this is valid, so that the decomposition takes place only on the surface, so it's a surface reaction rate control. So CVD is okay if it's under control, let's put that way. And in fact, so with many precursors that are used in ALD, so the limit between kind of a true ALD regime and CVD regime, so it's quite broad. So it depends, for example, on the fact, so how long precursor pulses you are using, whether the decomposition has time to set in or not. And that's important thing to keep in mind. So how we observe decomposition in these growth rate per cycle curves is something like shown here. So this is the pulse time for, in most cases, metal precursor. What we observe in the beginning is that there is a very fast increase of the growth rate towards the saturation level. And now if we are working under true ALD conditions, once reaching the saturation level, nothing more is being deposited. On the other hand, so if we are exceeding the decomposition limit, so we start to see this kind of a linear curves here. And of course, now higher the temperature, so more decomposition is taking place, and the higher the slopes of these then will be. But even in this case, so where decomposition is there, so one can reasonably well divide the growth regimes in two parts as a function of pulse time. In the beginning is this what is dominated by exchange reactions. So metal precursor reacting with the surface groups left, for example, by water pulse in the previous step there. And only once these exchange reactions are completed, more or less, the decomposition sets in. And if so, then if one wants to run this kind of ALD-CVD combination process still at higher temperatures here, so this is typically the pulse time range what one should be using. So that exchange reactions are completed, but decomposition is still kept minimum. Next requirement is that the precursors, they shouldn't etch the film or substrate. Because, well, if they are etching the film, so that will prevent the film growth more or less completely. At least it makes it very difficult to control. Unlike in CVD, or in CVD there is always, when we have a metal precursor, there is also some oxygen source available with which this metal precursor can react to deposit the film. In ALD we don't have. We have only the metal precursor and the film. And if these reactions like here, so this is one of the first our observations, niobium chloride, when that is pulsed over niobium oxide, it can form niobium oxide trichloride, which is a volatile compound. And actually, this reaction is so complete that one can completely etch away niobium oxide by using niobium pentachloride. But if trying to deposit films together with niobium chloride and water, so one has, well, very irreproducible result. And the same, for example, monoclinium chloride with molybdenum metal, and ozone with ruthenium dioxide producing ruthenium tetroxide. And the same requirement, of course, applies to byproducts. In case of metal chloride, so quite often HCl is being produced, and that can then react, for example, with the metal. A little bit related reaction, but not as detrimental as these etching reactions, are these exchange reactions, which mean that one is, for example, depositing nanolaminates consisting of titanium oxide and aluminum oxide using, in this case, aluminum chloride. So what happens once you have completed one layer of titanium oxide and you are able to deposit next aluminum oxide on top of that? So there is actually, at the interface, there is a replacement reaction, so that when aluminum chloride comes over the titanium oxide, so it replaces titanium in the oxide. Titanium forms now the volatile chloride, and aluminum oxide is deposited directly without reacting with water yet. But this is something, it's self-terminating reaction, so that after 10 ALD cycles of aluminum oxide, so no this kind of exchange reaction takes place anymore. But it's important to know that it's possible there, because that affects now the control of, in case of nanolaminates, these individual layer thicknesses. One gets thicker layer of aluminum oxide than expected based on the cycle number, or if making a mixture of two metal oxides. So this one, in this case, would mean that there would be more aluminum oxide in the mixture than calculated based on the cycle numbers alone. Sometimes we have also observed that there are problems that there is a dissolution of the precursors into the films, so they can destroy the self-limiting growth quite completely, what has happened in our first attempts to deposit copper by ALD. We used copper chloride and zinc. Originally it works pretty nicely, so that once we have copper chloride adsorbed on the surface, we bring in zinc, and this textbook kind of a redox reaction takes place, so that copper is being reduced, zinc being oxidized, producing zinc chloride and metallic copper there. So far so good, but once we have metallic copper there, so we actually start observing brass formation. So zinc dissolves into copper and forms brass, but this is not stable, so that during the following copper chloride pulse, actually zinc is diffusing out from the copper. So we have a zinc source there, the film itself is a zinc source, and that it reacts in a CVD manner with the copper chloride. On the other hand, sometimes this dissolution into the film or substrate actually may be very crucial to get the film growth starting in the first place at all. And for example, when there is a desire to deposit films on such polymers which don't have reactive functional group, so then this dissolution of one precursor into the polymer may help to get the film growth started or nucleated on this kind of a difficult substrate material. And as Ulla was shortly mentioning, so in case of these MLD processes, we have lots of possibilities to see this kind of dissolution processes taking place, especially if depositing porous materials where there is a void space where the molecules can go in. Again, something to be kept in mind carefully. Then is purity, and then here is a word, sufficient purity. So what is sufficient for the purity depends now on the application. Obviously, in semiconductor applications, purity requirements, they are higher than in, for example, in corrosion protection coating applications. And it's a kind of a, it's also important to understand that the ALD and also MLD processes, they are self-purifying. If there is some impurity in the precursor batch what you are buying, so it doesn't necessarily translate into an impurity in your film. There are two requirements for the impurities to get incorporated into the film. First of all, they need to be volatilized together with your precursor molecule at the same temperatures, and also they need to react or decompose on the growing film surface. Only then they will contaminate the film. In general, it's a good advice so that don't start with the highest purity precursors, paying more or less, or spending more or less your yearly budget for one single precursor lot. Start with modest purity, maybe 98%, it depends a lot what kind of compound we are talking about. See what comes out, and if then you start to suspect that purity may be an issue for reaching those functional properties you are aiming for, so then maybe once you are first validated that the chemistry is working, then perhaps increase the precursor purity, and together with that also the cost. But only if this is necessary. High growth rate, of course, very important. So now I'm meaning high growth rate in terms of angstrom per cycle. So the higher that is, so the higher will be also the overall throughput of the ALD process. In ALD, that typically means that one should look for small molecules, because once you have small molecules, so meaning small ligands, so you can pack more of those in the chemisorption layer than in case of you have very large ligands which take a lot of space there on the surface, and as a result, the metal-to-metal distance in the chemisorption layer would be very large, and the packing density of metals would accordingly be low. So here is an example about zirconium oxide processes. So these two curves here have been achieved with cyclopentadienyl compounds, and the third one here that is obtained with beta-dicatone. So these are not the smallest ligands, but still obviously they give higher deposition rate. In this case, this is a molecule which is actually not the zirconium THT, but it's a analogous cerium THT, and it shows that actually we have metal here, but around the metal there are lots of atom atoms as well. And now if you think about that, either depositing zirconium dioxide or cerium dioxide, out of these, all these atoms which are there in the molecule, only 3 are to be incorporated into the film. The metal and 2 oxygen atoms. All the rest are there just to make the compound volatile. Obviously then it's better to have smaller ligands and pack them more. And typically it also means that these smaller metal compounds, they show higher reactivity. But this is now the point where MLD becomes different from ALD, because in case of MLD, essentially all these atoms which are there in the precursor molecule are also left there in the film. And as a result, so in MLD, if you have large molecule and still can make it volatile, so it's quite often it translates to higher deposition rates as well, provided that there are no reactions from both ends of the molecule, as Ulla was also mentioning. Okay, but that was sort of what things I wanted to pick up from this list here. So there are some other things I didn't mention more, but I think these are quite self-explaining in most terms. So like non-toxicity and environmental friendliness and so on. I just wanted to add here so that this is really the complicated pair of requirements. One is struggling with while developing new ALD chemistry. So at the same time having aggressive reactions, yet keeping the metal precursors stable against the self-decomposition. Christoph was also showing this paper, or referencing this paper, so which is now actually it's out of date already. So it's something that the material was put together actually 2011. So it took some time to get it published. So there are some years in between, a lot of work has been taking place there. But already in this paper, so there we put everything together what we could find. So we have over 2,000, almost 2,400 references. So this lists 160 materials, 300 metal precursors, 780 processes. But now these numbers are much larger, and I wonder who will do the next kind of update to this one. And it's awful lot of work there. But yeah, I can also agree with him so that if you want to know what has been done by ALD before 2011, so this is the paper you should go through the table so and see what was available at that point. Of course, so with this amount of processes available, so I can only scratch a little bit and point out some general trends about ALD chemistry during the remaining 1 hour of my talk here. But let's start. So ideally, ALD, or actually ALD would be using only elements. So no worry about large ligands, no worry about small ligands. Just alternately pulsing these elements there. Unfortunately, we have only 3 metals, essentially zinc, cadmium, and nobody wants to touch it, but mercury is the third one. And these could be combined with sulfur, selenium, tellurium. These have been combined here. One could also add actually here ozone, for example, making corresponding oxides. But that's more or less. For all the other metals, so the volatility is not sufficient for most practical ALD conditions available. That's why one needs to use kind of a compounds as precursors for metals and also for the non-metals. I will now start with metal precursors. They divide in actually 2 groups. So first one is homoleptic, which means that all the ligands in the metal precursor, they are the same. So meaning that there is metal and then there are n times x ligands, but only one kind of a ligand. Then are heteroleptic complexes, which are also called mixed ligand complexes, for the reason that there are at least 2 kinds of ligands in the molecules. Now looking back to the history of ALD, I will do it in the starting very next slides. So the first metal precursors were homoleptic, for the simple reason that only homoleptic more or less were available at those times, mostly at least. But later, including today, so emphasis has shifted more and more towards the heteroleptic metal complexes, for the reason that by combining these ligands in a clever way, one can tailor the precursor properties quite a lot. On the other hand, so that also means that the synthesis of these molecules gets more complicated, and that is translated to higher cost. So these are, again, something Christoph was already showing. So this is from our Mammoth review, as we call it. So this is these tables are showing now the ligands which had been used at those days in ALD metal precursors. And in principle, so to design a metal precursor, so it's as simple as just select the right kind of a ligands here and combine those with the proper non-metal or organic precursor. But you can easily imagine so that the number of possible combinations gets very large here. And there are also synthetic limitations as said. So I will start now going through these homoleptic metal precursors. I will start from metal halides. Metal halides, to my opinion, they are severely overlooked precursors in ALD. People want to avoid, people are scared about metal halides for the reason that they are producing corrosive byproducts, they may be corrosive by themselves. But the fact is that these are, first of all, these are very low-cost precursors. Most of the other precursors are actually synthesized from metal halides. That's why these are cheaper than the other. They are starting materials. They show superior thermal stability. It's very difficult to decompose thermally metal halides. And they, in many cases, they show high reactivity. One important disappointing exception here is silicon tetrachloride, but silicon is also otherwise quite disappointing in ALD domain. But anyhow, these are corrosive. They are perhaps even more important. They produce HCl and other hydrogen halides as byproducts. One can live with these by proper choices in operating the reactors, choosing the materials there. Metal halides, so they exhibit range of volatility. Some of them are even gases, they are volatile liquids, they are solids which require source temperatures, in several cases what have been used in ALD, so below 200 centigrades is enough, so actually closer to 100 rather than 200. But sometimes one needs actually to go even to 500 centigrades, and that has been possible. Some of those are non-volatile solids which are not of an interest as precursors, unless you do something which I will show you shortly as well. So when Suntola and his co-workers, they started ALD in Finland, so they were very lucky to choose metal chloride as the first precursor. Or they chose metal precursors for the reason that there was hardly not too many alternatives, and these were again the cheapest ones to start. They started using metal chlorides and water and hydrogen sulfide in depositing oxides and sulfides. Motivation was coming from these electroluminescent displays. And very important thing here, again something which has been overlooked is in Suntola's achievement. So well, first he was verifying and demonstrating together with Sven Lindfors that the principle of ALD is working, but the next thing was to move to these metal chlorides, and to be able to use them they needed to develop this inert gas valving system. So that is in the next patent of Suntola there. And that made it possible to take these chemistries into industrial production of these displays. So this is 1978, so this is still very kind of a prototype reactor, but this is pretty close already what they have been using in display production. So it's P1000, with 1000 means that the diameter of the vacuum chamber is 1000 millimeters. So metal halides have been in production quite a long time already in making thin film electroluminescent displays there. And these displays, so the concept of these was known already in the early 70s, but for the reason that these are quite large area devices, obviously as displays are, and they require high electric field, so there was no reliable way of depositing these thin films for these displays with the existing technique like mostly PVD techniques. Also these are multi-layer structures, so that each of these layers is at least 200 nanometers in thickness. So the very first ALD application was not based on automated thin layers. Actually, these are one of the thickest layers in industrial production use of ALD ever. And especially this central layer here, so manganese doped zinc sulfide, which is the light emitting layer, so that is typically at least 1 micrometer in thickness. And these all colored layers, they are produced using ALD in industrial manner. In the beginning, all the precursors, they were metal chlorides. Nowadays they are using also some metal organics there, but still the chlorides are forming the main kind of a basis of this production scale use. And to exploit ALD in making this thick layer structure, so very important fact was that they were going straight ahead to large batch processing, which means that inside this kind of a reactor one can load tens of these displays as shown in the next slide here. And only by that way ALD could be proved cost effective enough so that it made it all the way into the display production. So ALD was really an enabling technique for taking electroluminescent displays in production, but it worked also the other way around. So now there was a factory where ALD was in industrial use. So it was taken there in mid-80s already. And that has been from my point of view, it's been a very important factor while then bringing ALD towards new applications, including also semiconductor applications. There has been lots of doubts about that. So how can you use this slope technique for anything industrially useful? And then we could always say that, hey, in Finland we have a display factory which is running with this technology already, has been running quite a long time there. And this is an interviewer view, so they have something like 50 ALD reactors in-house there. And that's the kind of a basic display structure there. Nowadays they have been developed completely transparent displays, so to the windows of cranes or harvesters, maybe to the cars, just by actually changing here where there is this aluminum metal electrode, so these have been replaced by indium tin oxide, so that all the layers in these displays are now transparent. And they are now very much promoting these displays to various kind of applications there. So quite several years ago already, so they exceeded 1 million display production number. And there was a talk about how slowly ALD films are growing, so I was calculating back of my head actually, so that what is the cumulative film thickness of these. So, and I think if you pile all these 1 million displays together, so you have more than 1 meter thick layer of film. On the other hand, if you calculate the volume of this based on the assumptions I rapidly made, so I came up to 30 liters volume of material. So this company has been in operation 30 years and they have produced 3 buckets of solid materials only. And they are still doing good business. Okay, so Christoph also said that in 2007 ALD went into the production into much larger application. That's true in high-gate oxide. But what he didn't mention there, because he was not talking about precursor, is that there the precursor also is a metal halide. It's hafnium tetrachloride, which is forming the core of the chemistry that Intel started using there. It was a very trivial thing because hafnium chloride is reasonably difficult to evaporate. The vapor pressure is 0.3 torr at 150 centigrade. And to get that operating, so ASM was working together with ATMI, as the company was called then. This kind of a special cylinder where there are multiple trays on which this hafnium chloride solid was loaded, and then their gas was percolating from bottom toward the top to pick up the vapor enough for the film deposition to take place. Anyhow, they made marathon tests and number of wafers shown here, and there was numbers were given out, so that because the hafnium oxides, they were something like 20 angstrom in thickness, so by loading 500 grams of hafnium chloride into this cylinder, so one could keep on running with that load 6 months in production environment of these gate oxides. And of course here very important thing is that hafnium chloride is so stable molecule that you can keep it half a year at this temperature, no problem at all about decomposition, so it could tolerate much more if needed. Okay, then I already said that there are some metal halides which are not volatile at all. Quite recently, so we went from these homoleptic metal chlorides to heteroleptic, so that we synthesized adducts of actually in this case cobalt chloride. We did the same actually also for nickel chloride. So cobalt dichloride is actually it's a 2-dimensional material, so it's infinitely long structures in the plane or in these planes, and as a result, so it's not volatile at all. But now adding a neutral ligand, which is this kind of a tetramethyl diamine, so shown here, so one actually is able to break the cobalt dichloride structure and make monomeric units. And because these are monomers, so they are volatile. And they show reasonably nice behavior in TG, and we could deposit cobalt oxides using this kind of metal halide adducts. And I'm sure there are lots of room also for developing corresponding systems for many other metal halides, which in general are considered non-volatile. Earlier, actually, Air Liquide was dealing with the problem of tantalum chloride being a solid. So they made this kind of a thioether adduct of tantalum chloride. They converted that into a liquid. It had very little effect on the vapor pressure, but it changed the phase to the more desired liquid. Okay, after the metal halides, so I guess the next group of precursors quite extensively studied in ALD were metal alkoxides. So Ulla was talking about alcohol molecules producing these alucones and related materials. So in this case, so these are monoalcohols, and they are now rather good volatile compounds. Quite limited choice of metals, however, in this case, but especially for titanium, tantalum, niobium, these have been perhaps even dominating precursor types in ALD in general. Aluminum alkoxides are pretty good as well, but there is a TMA, so there is not so much interest to have alkoxides for that reason. We also, earlier we studied quite a lot alkoxides for zirconium and hafnium. They are not so stable, or actually they are poorly stable, but with donor functionalization, this stability can be improved, but at the same time also the reactivity goes down. There are also some works about using double metal alkoxides for depositing these materials, and one can use lead alkoxides at least for sulfides as well. So with these donor functionalized alkoxides, so well, actually I was already showing the example with the tantalum, so that besides having the alkoxide functionality, there is one donor or several other donors in the molecule as well, and as a result, so one can increase the coordination number and by that way improve the stability volatility. Metal beta diketonates, yeah, they have been around already from essentially from the beginning of ALD, actually even before ALD was developed, so metal beta diketonates were used for other purposes. I think this is a group of compounds which offers you the widest selection of volatile metal compounds. So essentially all metals can be made volatile by choosing beta diketonase ligands, which are bidentate oxygen donor ligands, so making 6 rings, very stable molecules. The main problem here is that these are quite large molecules, which means moderate growth rates. Also, in case of oxide deposition, they don't react with water, but require something more aggressive, especially ozone, oxygen radicals from plasma. And at that time, they also lead to a risk of carbonate formation. They show, in many cases, better reactivity towards hydrogen sulfide than towards water. And they can also be used for depositing fluorides and metals, as I will show you a little bit later. Metal alkyls are, in those cases where they are available, they are really useful. In ALD field, so it's mostly aluminum, zinc, and cadmium where these have been used. And out of these, aluminum, zinc, of course, they dominate over the cadmium, which has these concerns related to its toxicity. These are the main materials deposited from these. It would be quite tempting to just go down in the same period, in the same group in the periodic table from aluminum to gallium and indium, but I would say that in general these have been quite kind of disappointments in a sense, so that the high reactivity what aluminum molecules is exhibiting, so it's quite much less for gallium and indium. These were studied quite extensively there in the late 80s, early 90s, where there was a lot of efforts towards exploiting atomic layer epitaxy, as it was called those days, for making 3,5 compounds like gallium arsenide and so on. Trimethyl aluminum, well, it was mentioned already, but it is really the ALD precursor. If all precursors were like TMA, so we would be in much better position taking ALD to new application areas. But they are not. But this is really something, it's setting the requirement or the goal, so what we would like to have from ALD precursors. Volatile liquid, high reactivity with various kind of things, co-reactants, unreactive byproducts being produced, available in relatively low price. Main problem is that it is pyrophoric, but that's a sign of ALD reactivity. One thing which is not necessarily so obvious and so well known about TMA is that it's quite reductive by its nature. So it's good if one wants to make conductive nitrides like tantalum, aluminum nitrocarbide. I will come back to that later. It's also exploited what is called self-cleaning effect nowadays when depositing oxides on 3,5 compounds, which typically they have their native oxide, like gallium arsenide is partially oxidized from its surface. One pulse of TMA removes the oxides because aluminum is eating the oxide away there. So this is kind of a good thing. The problem is that if you want to make high quality mixed high-K materials where you are mixing aluminum, especially with such oxides which aren't quite readily reduced, like titanium for example. So TMA is to some extent reducing titanium, and by that, while doing that, so it's creating defects there, which then are deteriorating the insulating properties. But this can be compensated at least reasonably well by using strong oxidizer of ozone in the process. Next group of metal precursors which came available, I think this, of course, things have been taking place parallel and with each other, but roughly speaking at least, there were metal cyclopentadienyls, which are again quite versatile group of precursors for certain metal oxides. And then alkaline earths were very important in that respect, also lanthanides. To some extent they also work for sulfides like strontium and barium. They can be used also for zirconium and hafnium, but not in homoleptic form. And it was kind of a continuation of this exploration of cyclopentadienyl compounds, which then led to various kind of heteroleptic precursors later. And I'll come back to those when I get to the heteroleptic part. And nowadays also noble metal cyclopentadienyls are used quite a lot for depositing metals. Our work on cyclopentadienyls really started from this process for strontium titanate, so that was in late 90s. So we were requested to develop ALD process for this strontium titanate, which is a very high K constant dielectric. There was a good process, several good processes for titanium oxide available at that time, but for strontium we didn't have good choices. There was only strontium THD, but that wasn't reacting with water if we were using ozone, so carbonate contamination was a risk, and that's why we then came up the idea to test cyclopentadienyls there. Timo Hatanpää synthesized the compound, it was characterized, verified to be what it was supposed to be. We took that into our growth experiments and proved that we can do nice conformal strontium titanate films with this chemistry. And ASM, our close collaborator, then scaled it up to 300 millimeter processes in their pulsar reactors with reasonably good uniform. Still a couple of homoleptic groups in general. So the next one is where we have a nitrogen donor. So they are either alkyl amides or silyl amides. In both cases there are metal nitrogen bonds. And again, quite versatile groups, lots of possibilities for various kinds of metals, but still reasonably limited use has been there. And the problem in quite many cases has been the limited thermal stability. Compared to those compounds where oxygen is the donor bonding with metal, so these are not as stable, at least in most cases. So zirconium, hafnium, they have been extensively used in making these corresponding high K oxides, but also in this case the thermal stability is limited so that up to 250 they are stable, but when going to higher temperatures, so one doesn't see any more complete saturation but CVD component. In case of titanium, the decomposition sets in even earlier. We have used this, for example, for lanthanum, but problem in case of silyl amides is that silicon can quite easily also get incorporated into the films. And one example is to use silyl amides was for making these kind of various kind of bismuth-containing films, and there the key was to use this as a ligand for bismuth. And then final example here is about these homoleptic compounds, is metal amidinates. So this is quite well known also like kind of a Harvard chemistry, because it was Roy Gordon's group in Harvard who introduced this kind of a ligands in 2003. in their first paper in Nature Materials, they showed several processes for oxides, nitrides, but also for some metals, and then later also for sulfides. And then what we have seen later is that these really are kind of a multi-purpose ligands for many oxide processes, but unfortunately the repetition of these metal processes has, well, it's been very difficult. Obviously, there are very few reports in using these in depositing metals. The idea here is that, well, the amidinate benefits are that the nitrogen metal bond that's stronger than carbon metal bonds in most cases. There is a chelating effect, so there are two donor atoms here, so chelates are always adding to stability. On the other hand, so this bonding should be weaker than in case of metal oxygen bonds, and so this should be a kind of intermediate group of ligands between these alkyls and oxygen donor ligands, and indeed it seems to be there. Okay, but now I move on to the heteroleptic metal precursors, even if I already to some extent have visited that every now and then already. But the motivation now is really to combine the best properties of the corresponding homoleptic complexes, and also to exploit such ligands that can be used in homoleptic complexes only. So there are lots of examples of those as well. In principle, you remember the table with various kinds of ligands, and if you can choose 4 of those, you can make a countless number of combinations. The problem or the question then is who is synthesizing these all. So there are limitations coming, what can be synthesized, and of course what can be transferred into the gas phase. So there may be that you are able to make certain heteroleptic metal compounds once you start to heat it. So there are ligand exchanges which are actually breaking it down to the homoleptic compounds and so on. But one example shown here is titanium isopropoxide. So that's reasonably stable. 280 has been quoted as a limit in this case. If there is a desire to go to higher temperatures, by changing 2 of these isopropoxide ligands with THDs, producing this kind of a molecule, you gain 100 centigrades in thermal stability. On the other hand, so at this point there are addition of these beta-diketonates which are not so reactive with water molecules. Most likely, we don't have our own experience on this compound, but most likely you are losing at the same time now in reactivity with water. There are lots of heteroleptic precursors available. I've chosen now zirconium and to some extent also hafnium oxide as an example only to show what has been, how the evolution has gone there. So if looking back, the homoleptic precursors for zirconium, so basically 2 compounds were dominating. Zirconium tetrachloride, it's a solid, it's a corrosive, causes some concerns to many. On the other hand, there were zirconium alkylamide, which has a limited thermal stability somewhere to 250 centigrades. Then, this was somewhere around 2005, and after that, so there was a look on the cyclopentadienyls. One can make homoleptic cyclopentadienyls for zirconium, but heteroleptic. And in the first one, so there were 2 cyclopentadienyls, 2 methyl ligands here. This could be used with ozone or water, producing rather pure films at higher thermal stability compared to zirconium alkylamide. But there was a problem that this was a solid. So the next step from here was that one of these methyl groups was replaced with a methoxide group. So now we have actually a metal complex with 3 kinds of ligands. And this is now turned out to be a rather good precursor. It's a liquid, stable up to 400 centigrades, so it's nice with saturation there, and gave rather good film growth as well. This being learned, so then the thinking was so that, okay, we have cyclopentadienyls which have this higher thermal stability as shown here, but the growth rate were still, well, they were leaving room for improvement. It was also known that alkylamide, so they do exhibit this higher deposition rate, but they suffer from low decomposition rates. And then the question is that if we combine these, so can something better be created? And Air Liquide was synthesizing the range of this kind of complexes where there is a 1 cyclopentadienyl with a substituent or without substituent, and then 3 alkyl amide ligands, and these are the simplest examples shown here, and also in reasonably good volatility. We were then testing the simplest of these, so unsubstituted cyclopentadiene here, and these three dimethylamine ligands, and we compared that against the alkyl amide alone. And this is, well, we saw this curve already. At 300 centigrades, there is no saturation with the alkyl amide, but with the CP heteroleptic compound, there is the saturation. And the saturation is now to a higher level than in the previous CP compound, so it's about 1 angstrom per cycle level. And with very nice step coverage in aspect ratios of, I think these were 80:1 or 60:1. And this turned out to be a very valuable compound for Air Liquide. So they are selling that with a brand name of Dual. And I think the annual turnover produced by this one single molecule is approaching somewhere to 100 million euros. And it's used worldwide in making DRAM capacitors. So it's and now if you think about what is the value of DRAM market, so it's expected to exceed this year 100 billion $100 billion. And it's very much backed up by this heteroleptic compound, so Air Liquide was originally synthesizing and we were testing. Oh, we have still continued from that on, so these are some examples about compounds that have been synthesized in our group, so showing, well, certain success. These, now we have here cycloheptatrienes, or larger rings. In these cases, so the metals are so well protected by the ligands so that they are not reacting anymore with water, but they require ozone. And the story is still continuing, so this is a paper we have again produced together with Air Liquide, so just to show you that only an imagination is a limit, so what kind of ligands can be added there. And in this case, so we got pretty good results, so about good thermal stability with some of these compounds, but don't want to go in further in details here. Okay, so that was the metal precursor side. But of course now, when talking about ALD, so we need the other reactant either for making compounds or, in case of metal, so to reduce the metal in the metal compound, metal precursor. And now I will make some overview about these. And there are much less of these, but it's also one could think about that it's much, and indeed it is to, in that sense, so it's also a little bit clearer for you than the metal precursor. But there are lots of flavors here as well, so it's not so trivial one might actually expect. Oxides have been dominating in ALD of compounds, and as a result, so I start from oxygen precursors. And most of the ALD oxide research has done by using one of these three, so either water, ozone, or oxygen radicals, or oxygen plasma. Water is nice in a sense so that those metal precursors which are reacting with water, so one can consider these reactions pretty clean, so that the ligand is removed from the metal by simply and nicely protonating. And as a result, so the ligand stays intact. So there's a transfer of hydrogen from the water to this ligand. It forms methane in this case, and it goes away. The problem is that not all metal precursors are reacting with water at all. So especially beta-dicatenates have been a problem, but also some of others, as we just saw. On the other hand, so when ozone is being used, so then essentially always it means that the ligands are more or less completely combusted, so that they are not anymore staying intact, but rather there is a formation of carbon oxides, water, which as such is not a bad thing, but there is a big risk so that some of these fragments may actually remain in the films, especially if the film has a tendency to form carbonate. So there is in that sense, so there is a risk of carbon contamination of the oxide, which needs to be taken into account. What was also a limiting factor taking these chemistries into high-K oxide deposition is that ozone is not only reacting with metal precursor, but it's also reacting with the silicon surface when depositing these high K oxides on the surface of silicon. And this is it's been deposited using ozone. This has been deposited by using oxygen plasma. In both cases, there is at least 10 angstrom of silicon oxide on the surface, and this is essentially a showstopper in using high K oxide. So this is too thick for the gate oxide stacks, and that's why there has been a need to use water-based processes for those. Alcohols, hydrogen peroxides have been used to some extent. We came up to the idea of using actually metal alkoxides as oxygen precursors at some point for this actually same reason. So that our thinking was that now in this case oxygen is bonded very strongly already to silicon, and as a result, so it's not available there to oxidize the substrate surface there. And indeed, it seems to be working pretty nicely. Unfortunately, these reactions, they are not so complete as one would desire to have, and there are some residues being left in the film. But anyhow, it shows that some idea that by combining two metal precursors, one can actually create a working oxide process. Then talking about other non-metal precursors, so hydrides dominate still. The main problem here is that quite many of these hydrides, they are actually toxic. And one either needs to live with the fact, with some safety measures there, or a lot of work has been done also to look for alkylated derivatives for lower toxicity. Unfortunately, when these hydrogens are replaced by alkyl groups, one is also losing in reactivity quite a lot. But then there are some other options. I'll come back to these in the next slides before going there. So I want to point out that there are lots of possibilities now to use these non-metal hydrides and also some other non-metal compounds when they are activated with plasma. So hydrogen-nitrogen plasma and ammonia plasma have been used for nitride deposition, while oxygen plasma I already mentioned earlier, but one can also use water hydrogen sulfide plasma as we have seen later. So now I go to the alkyl silyl compound. So this is again a story from our group. Our collaborating company requested us to develop chemistry for depositing germanium antimony telluride compounds by ALD because these are potential phase change memory materials. At that point we know out of these three elements that they have been poorly studied in ALD, and what so far has been learned was that they are difficult in ALD. And we were quite skeptical about our possibilities to develop this kind of a chemistry, but then we came up to the idea to use this alkyl silyl. Well, we started from tellurium because that was in the main focus, but also the same works with selenium, these compounds. And it turned out that they are reacting quite in general with metal chloride compounds. So not only germanium antimony, but many other metal chlorides were reacting with these as well. And this is actually a pretty nice demonstration about this, which is a basic chemistry concept of Lewis hard soft acid base principle, which explains the reactivity. So in this concept, so one is dividing elements to hard and soft, either acids or bases, and the principle relies on the fact that hard combination and soft combination, they are much better than hard hard combination. And now looking these compounds here, so silicon is a hard Lewis acid. It's bonded in this case to tellurium, which is a soft Lewis base, so this is unfavorable condition. Then there is a metal, which quite often they are in this case, so we are talking about quite soft or borderline Lewis acids at least, and chlorine is hard or pretty close to hard base there. And when the reaction takes place, so one actually gets a borderline soft combination and hard combination, and the principle teaches us that this should be a working chemistry, and indeed it turned out to be working chemistry. And it was developed with motivations coming from the germanium antimony telluride. We studied that further, also the material properties with IBM, and it's working, or the functional properties are as expected, similar to the sputtered counterparts, but with the added conformality of ALD technique. But once we have the chemistry available, it could be extended so that, for example, bismuth selenide tellurides could be deposited for thermoelectric applications. We went further on and also made some similar compounds for antimony that reacts with metal chlorides to deposit metal antimonides. But quite interestingly, this opened also a possibility to a very unique elemental ALD process. So now by choosing antimony chloride and this triethyl antimony compound, so there was a reaction that can be classified as a compropionation reaction, which resulted in deposition of elemental antimony in very conformal manner through the elimination of this triethyl silicon chloride as a byproduct. Then, this is a little bit odd statement, that's why I add this guy with the question mark. So we have also studied a chemistry where we use metal halides as halide precursors for metal halides. So what that means essentially is that we choose one metal halide which is a volatile, and then we use that for depositing such a metal halide which is definitely not volatile. And there is an exchange reaction so that calcium, in this case it's a beta dicatonate compound, it's alternately pulsed together with titanium tetrafluoride. There is an exchange reaction which for sure results in deposition of calcium fluoride that we analyzed inside out. And our speculation is that the byproduct is simply a titanium THD. It may be also some heteroleptic form of titanium fluoride and THD, we don't know that for sure. But anyhow, so this is a chemistry which is very nice with depositing the calcium fluoride and also other fluorides. And just this year, actually, Georgi Popov gave a presentation in the ALD 2018 conference where we did the same with iodide. So now there is a thin tetraiodide is the volatile metal halide compound, and when it's reacting with this lead compound, so it produces lead iodide. But only at very low temperatures, because actually this lead iodide, that this metal halide is also a volatile. It has been earlier used as an ALD precursor, but working below 100 centigrade, so one could deposit pretty nice lead iodide film through this exchange reaction. And we have used the same also for lithium fluoride, so lithium THD plus titanium tetrafluoride. And actually, quite interesting thing here was, there was a little bit talk about conversion reaction. So here we exploited a conversion reaction as well. So these direct lithium fluoride processes, they are a little bit tricky to control. So therefore we had a look also on the possibility that we first use a very robust process which is depositing magnesium fluoride, and then just expose this magnesium fluoride to lithium THD. And the magnesium fluoride was 170 nanometer in thickness, and with increasing number of lithium THD cycles or exposures, so it was completely converted from magnesium fluoride to lithium fluoride. So all the magnesium was converted away through these reactions with lithium THD. So this is kind of an unconventional looking non-metal precursor. If you want to see more, actually ASM has been working with this already 10 years ago. There is actually quite good review paper by Wei-Ming Li from 2013. But this shows different kind of compounds where the focus is now what are the non-metal elements there, and on the other hand, so what kind of precursors have been used there. For example, this tungsten nitrocarbide they have studied a lot. So here they use triethyl boron and ammonia. No boron left into the films, but carbon get incorporated, and so on. But again, something I don't have time to go in detail, but just to want to point out that there are quite a lot of possibilities in exploring this. Then reducing agents. This is of course something we need when we want to deposit elemental films. And well, we had the lucky unique case of antimony earlier, but here is I like to use tantalum as an example here, because tantalum exhibits different oxidation states in its various compounds. So starting from tantalum pentachloride, so of course tantalum is +5. Now using nitrogen precursors, one can end up either having dielectric tantalum 3 nitrogen 5, so this is still +5, or conductive. This is normally tantalum +3, or one can go all the way to the metallic tantalum. So basically now by comparing different reducing agents, one can rank them, so what is the reductive power in ALD conditions. For example, with ammonia or dimethylhydrazine, there is no reduction taking place. If one adds elemental zinc, so one gets metallic tantalum nitride, but nobody wants to have zinc in semiconductor environment at least. Then there are alternative reducing agents like trimethyl aluminum. So trimethyl aluminum is producing well-conductive tantalum aluminum nitrocarbide. If you think about this phase and aluminum carbide phase is alone, so they are both insulating. So that shows that in this case, DMA is reducing tantalum. And eventually then when going to plasma conditions, so one can produce tantalum nitrides with controllable X there, and with hydrogen plasma also elemental tantalum, at least with some level of success. In metal ALD, so a lot of different reducing agents have been studied. Kind of bad news here is that there is really no universal reducing agent, unless perhaps considering hydrogen plasma as such. But in some other cases, so there are quite well working options. Now in the coming slides, I will talk about these noble metal processes. So in these noble metal processes, it turned out that by using molecular oxygen, one is able to deposit elemental films, which is a little bit against kind of what you might think. So oxygen should result in oxide deposition, but it doesn't work like that. Well, one explanation for that is that these are noble metals which are forming low stability oxides, if forming oxides at all. And these metals have been deposited now using O2 molecule as the co-reactant there. Important thing is that these are catalytically active metals, so that they are activating the otherwise quite inert O2 molecule by dissociating that to atomic oxygen. And then it's reacting with organometallic and beta-dicationate metal precursors. So Petra and Aaltonen started this work, and then ASM was scaling it up to 300 millimeters quite rapidly there. And since that, so it's been expanding, I guess, worldwide in quite wide use in ALD field. So we have used quartz crystal microbalanced mass spectroscopy to study the chemistry there. Without going further in details, there is just one surprising thing which I want to point out in this ruthenium process. So we have cyclopentadienol and O2. And with quartz crystal microbalance, we see that once we are giving a pulse of rutenosane there, for growing the ruthenium film, we actually see mass coming down. And when we then give oxygen pulse there, we see mass going up even if we use oxygen to remove the ligands from them. So what is explaining that is a mechanism which is shown here. So by carefully start using this data from mass spec and quartz crystal microbalance, we came to this kind of explanation that after the oxygen pulse in the process, so we have atomic oxygen on the surface, but also in the subsurface regime on the ruthenium film surface. And now when the ruthenium precursor comes here, so all these atomic oxygens, they are reacting with ligands, producing CO2, water, as we saw with the mass spec, coming out during both pulses here, leaving still some hydrocarbon fragments and adding the ruthenium metal. And then during the oxygen pulse, so oxygen molecules, when they come there, so they dissociate, forming atomic oxygen, which combusts less of the hydrocarbons away, and then recharges the atomic oxygen on the surface and in subsurface regime. And now, even if we are adding ruthenium atoms during this step, so we are removing so much of this atomic oxygen that the net effect on the film mass is actually a decrease. So more oxygen atoms are being removed in mass than what is being added on top, and the vice versa then during the next pulse. So even if hydrocarbon ligands indeed they are removed here, one adds so much oxygen that one sees the mass increase during this pulse here. Okay, then we have extended this chemistry further later by now replacing oxygen with ozone. That made it possible to deposit also noble metal oxides at low enough temperatures where these oxides are stable. On the other hand, when going to higher temperatures, we actually got metals also with ozone. And this shows some example about how one can tune with the resulting film composition using oxygen, ozone, and hydrogen in proper combination. So iridium acetylacetonate, so beta dicatonate, so that reacts with molecular oxygen only about 225 centigrades, producing metallic iridium. But if one now uses ozone, at those temperatures where it doesn't react with O2, so one is able to deposit iridium dioxide. On the other hand, when exceeding 200 centigrades, with ozone also we get metallic iridium. But if we then do so that we have first iridium acetylacetonate, then add ozone to make iridium oxide, and next step give hydrogen pulse, so we are reducing the iridium oxide. So we can lower the deposition temperature to 165, so deposition temperature of metallic iridium. Otherwise it requires at least 200 centigrades. This 165, so its limitation was coming from the iridium acetylacetonate source temperature. But then we went further on and we developed a new iridium precursor, so a heteroleptic compound that we could evaporate at lower temperatures, and then we could also lower the deposition temperature of metallic iridium down to 120 centigrades by using this new metal precursor, ozone and hydrogen. So by playing this chemistry both on the metal and non-metal side, one can tune the proper deposition conditions for metallic iridium. And finally, the ozone chemistry eventually came into our sort of a dream, so we eventually could deposit it cold, so that has been kind of a passion for us quite a long time, so to deposit metallic cold by ALD, and it required a synthesis of, I guess, 20 cold precursor candidates, and eventually we found one which is thermally stable enough so that we could volatilize it nicely. It doesn't decompose until 250 centigrades, and once we used that together with ozone, so we could deposit cold films in a saturated manner at 180 centigrades. Okay, so I also had some plans to talk about what are the motivations for developing still new ALD chemistry after 40 years behind. I think these are quite self-explaining if you go through this later. Maybe just want to point out that eventually when ALD, when it's going into production, and Paul is going to talk about that after the profit break, I guess, really the cost becomes a factor. So no matter if you go to this kind of a batch tool, so this is a tool where one man can walk inside. So this is a precursor-hungry tool, so it means that the cost is getting more and more important. I guess Paul is talking a lot about the spatial tools, the same thing here as well. But of course then, the previous list was for such compounds where we already have ALD processes available. There, in most cases, there is still a good amount of room for improvement in one of these or several of these points listed here. But of course, kind of a scientifically even more exciting is to add new materials to the ALD material portfolio or process library, no matter how you call it. And here, well, it depends who you ask, or what are the designs, what kind of a processes, what kind of material should be added there. One thing is for sure, what is expected from this group here is to add new MLD processes for organic and hybrid materials, and that's definitely in our focus. How to get there? So, well, you can have a new chemistry on all points here. Metal precursors, non-metals, organics, reducing agents, other assisting reactants, combining these, also combining such compounds which have been around in ALD or MLD already, but combining these old things in a new way, and also use conversion reactions. So to conclude, so I could say that the ALD is a unique technique. If we look at the precursors against CVD precursors, there are lots of similarities. The difference comes from the way how they are combined in ALD as compared to CVD. So in ALD, we are really looking at the most aggressive combinations to get things proceeding fast and efficiently as designed. Quite many of these processes which are reported as ALD processes, they are not exactly fully ideal ALD processes. We have weak precursor decomposition, other unwanted side reactions. These are okay, but these need to be compensated then through reactor design if existing. During the past 10 years or so, the precursor development for ALD has gained a lot of effort, also from the big chemical manufacturers. So Liquid, which was several times mentioned in this presentation, is only one of those big companies. There are many others who are working now, because there's a lot of incentive coming from the precursor market here. On the other hand, so this applies mostly to ALD chemistry. MLD is still coming, so this is a very great moment for you to start your career on MLD chemistry. There are lots of new things still to be found out. And to assist this development both on ALD and MLD side, so I think it's very important also to carry out these fundamental studies on what is really happening on the film surface, how the reactions are proceeding there, to understand the main reactions, understand the side reactions, both by experimental and computational means. Okay, that was all I wanted to say. I had time to say to you, and thank you very much for your attention.
Thank you very much. Any questions? Maybe one question myself, just out of curiosity. You mentioned for MLD that a lot of the precursors are quite bulky, and so volatility might be an issue.
Yeah.
In recent years, amongst others, I think particularly Julian Wachman has been publishing some papers on liquid phase processing. Could you maybe very briefly give your opinion on that type of development and pros and cons?
Yeah, there's, well, first of all, there has been liquid ALD long time around for inorganic material, so it's been called mostly as SILA. So successive ionic layer absorption and reaction. So it's been taught over the decades already for the inorganics. For organics, yeah, it's a very interesting concept. And I've been thinking also, so how much freedom we have within HYCOAT to go into liquid phase in case we identify molecules which seem to be very attractive from the reactivity point of view, but we can't volatilize them. So it's, yeah, so it's, on the other hand, so I think ALD kind of chemistry carried out from the liquid phase has been around also otherwise by lots of different names. So there is quite a lot of this kind of a click chemistry between solid phase and liquid phase that's been available, and this is at least it can serve as a guideline for us, so that to have a look so what kind of reactions have been exploited in those cases. It can also kind of be as kind of a plan B in case of not having the volatility there. So yeah, it's a very important point to add and keep in mind, so that one can also do this through liquid phase. Of course, we know also from the SILA, so this inorganic liquid ALD world, that if ALD is slow, that's awfully slow. So we are talking about cycle times which are maybe 100 times longer than in here. Marco may want to add something.
Yeah, so I want to add so that in this inorganic SILA, so we used to have water solutions, and then we have like a purge, which is washing in water. There is a version where the washing step is taken away, so they call it Ilva. Always people have their own names, but that is what in MLD could be talked about, so that we have organic solution where we have the component that we maybe do not need any washing there in between, and that makes it faster. But anyway, so it is slow still, and also that the reaction are not that complete because it's usually room temperature. So, but definitely we could in MLD.
Yeah, this ILGAR was so that they were dipping into metal solution and then exposing to H2S vapor.
Yeah.
But there is also other way around, so that one has a metal precursor from vapor phase, and then liquid water was added to hydrolyze it. So yeah, that was called valid.
But indeed, maybe as a plan B.
Or it's a plan D already. I guess.
Other question?
Maybe for precursor chemistry, so most of the precursor chemistry studies were analyzed either experimentally or modeling as if like the molecules are floating in space. But I haven't seen like a rigorous study like employing say a measure on how it actually saturates or reacts on the surface. And we actually have an SI unit for this, which is Langmuir. But aside from some papers with Air Liquide, I haven't really seen a standard parameter or parametric methodology to kind of account for this. So do you have any views on this?
Well, I think Christoph was showing what these three curves you are expected to show when you are developing ALD chemistry is these saturation curves. They are as a function of time rather than dose, and I think there is a good reason for that. So when you are talking about Langmuir, so it's a pressure time times the time of exposure. But in ALD chemistry, so our reactions, they are so fast that at the point when you reach a stable partial pressure with your precursor, you are done already. So when you bring TMA on a surface which is hydroxyl group terminated, everything will react first. And it's very difficult to say what was your partial pressure when you were doing this, realizing this saturation. And only once you have saturated the surface, so then is the pressure, partial pressure of TMA able to reach a stable level in the chamber. I think it's also a sign that if somebody is showing the exposures in terms of Langmuirs, so it's usually an indication that this is very slow ALD chemistry. And that's in the SiO2 ALD processes. There are these Langmuirs, and if you calculate out of those, so that what would be the exposure time if you guess that the partial pressure might have been 1 torr or 10 torr, so you easily come to exposure times which are 100 seconds or so, as opposed to 1 second with other chemistry. Your statement is valid, but there are good reasons not to do so.
How do you decide the nature of the coating that you need to apply?
How do we?
Is it a trial and error, or is it what is the previous step before doing?
Well, it usually starts from application. So there is certain functionality that is expected, and that usually is translated in several parameters. And based on these parameters, we do our choices. And the first thing usually is to try with the existing ALD material. And quite often we start with aluminum oxide, right? So, but there may be a good reason not to do or so. But yeah, it's a very broad question in that sense. So, but I think when companies are approaching us, they know very well what they want. Then we try to convince them that they should want something different, maybe something that we can do more readily. And yeah, sorry, I don't have more exact answers to that.
Thank you.
Other question? That's time to speak.
Okay, thank you.
This morning I forgot that we had a small